Hello everyone, thank you for attending this talk. My name is Maaz Ahmad, and I will be presenting our work on vector instruction selection for digital signal processors using program synthesis. This work was done in collaboration with A.J. Root, Andrew Adams, Shoaib Kamil, and Alvin Cheung. Instruction selection is a key phase in any optimizing compiler, whereby expressions in the compiler's intermediate representation are translated into executable instructions from the target platform's instruction set. Unfortunately, when targeting modern vector instruction sets, choosing the optimal sequence of instructions can be extremely difficult. Not only do these instruction sets include a rich set of complex intrinsics, but the optimal implementations often require an intricate interweaving of data movement and computation. The traditional approach to instruction selection, and perhaps the most widely used still today, is based on pattern matching. This approach relies on predefined transformation rules to do the translation. For instance, consider this sub-expression in our example that computes a rounding shift right narrow of the input value. To optimally translate this sub-expression, we can add a rule to our compiler that maps this pattern to the rounding shift right narrow instruction in the target instruction set. The problem with this rule-based approach is that not only does it require the compiler developers to have the necessary foresight to generate the correct set of rules, but that these rules tend to be brittle. For example, here's another expression that computes the rounding shift right narrow of the input value. While the optimization rule worked for the original expression in green, it would not work for this new expression in red simply due to the syntactic differences between the two implementations. Furthermore, pattern matching often fails to detect context-specific optimizations that require semantic reasoning. Consider the case where the target instruction set does not actually have an instruction that implements the rounding shift right narrow pattern that we need, but it does provide an instruction to do a rounding shift right saturate. A human engineer optimizing this code by hand may be able to realize that the value computed after the shift right operation is always small enough to actually never overflow during the cast step. This implies that using the instruction that performs a saturating narrow instead of a truncating narrow does not actually change the semantics of the input code. On the other hand, pattern matching being a syntax-driven approach as opposed to a semantics-driven approach will fail to discover such optimizations. An alternative approach for instruction selection is super-optimization. This approach, rather than rely on predefined rewrite rules, attempts to simply enumerate the programs in the target instruction set, searching for a program that is both correct and has the lowest cost. Although this process can generate optimal implementations, it has limited scalability due to the combinatorial complexity of the search problem. Therefore, in order to scale to larger programs, state-of-the-art super optimizers typically use a sliding window decomposition. Since the entire program or expression may be far too expensive to optimize together, they restrict each optimization query to a small window of instructions that are then optimized locally. Sliding window decomposition allows super-optimizers to scale to arbitrarily large programs, but it is not well suited when performing instruction selection on modern vector instruction sets. For starters, modern vector instruction sets contain complex intrinsics that implement patterns that can be up to 15 or even 20 operations long. These patterns are actually larger than the window sizes that these state-of-the-art super-optimizers actually support. And even if the size of the sliding window was large enough to contain the entire pattern, there is no guarantee that the entire pattern will actually fall within the same optimization window. Since each window is optimized locally, the super optimizer may not detect opportunity to use these powerful intrinsics when the pattern is split across adjacent windows. Finally, these sliding windows are an arbitrary grouping of instructions. They provide no semantic insight into what each code block does. Lacking any insight, the super optimizer must then naively search the space of all possible instruction sequences, which is very expensive. This brings us to Rake, a new, more scalable synthesis-based algorithm for instruction selection. The key observation behind Rake is that rather than decompose expressions into arbitrary windows, what we really want to do is group operations that together implement a higher-level compute pattern. For instance, we can decompose this input expression into these two groups. The operation in the first group implement the high-level rounding shift right narrow pattern, whereas the operations in the second group implement the higher-level multiply add pattern. There are several advantages to such decomposition. For starters, the size of each operation cluster is elastic, and we will avoid instances where the pattern that could have been implemented as a single fused intrinsic was being split across multiple optimization scopes. Secondly, this decomposition exposes higher-level semantic information about each group of operations. We can use this information to refine our search. For example, when synthesizing an implementation for the rounding shift-right subexpression, we can restrict the synthesizer to consider only the subset of intrinsics that perform relevant operations, such as shift-rights, rounding, casting, or addition, and ignore all other irrelevant intrinsics, such as vector reductions or I/O instructions. To implement such semantics-based decomposition, we need two things. First, we need to identify what are the set of high-level compute patterns that we want to base our clustering on. And secondly, we need an algorithm that performs the clustering. For Rake, we derive the set of high-level compute patterns from the target instruction set as a set of uber instructions. An important realization we made when designing this instruction selection algorithm was the fact that most vector instruction sets contain a large number of very similar instructions. For example, here's a subset of all instructions provided by Qualcomm's HVX architecture. We have the add instruction that adds the elements of the two vectors together. We have a multiply add instruction that multiplies the elements of the first vector by a scalar before adding it to the second vector. And we also have the toMultiply add instruction that multiplies the elements of both vectors before summing the results together. If we rewrite these expressions slightly, we can see that both the add and the multiply add instructions are merely specializations of the more general toMultiply add pattern. In fact, we can view all three instructions as a specialization of the even more general nMultiply add pattern. And it gets worse. In the full HVX instruction set, each of these instructions have multiple variants for handling different integer types. They also have widening and non-widening variants, and we even find variants that specialize for different input vector layouts. Given an instruction set, such as this one, we first identify the set of instructions that have similar or overlapping semantics. Then, for each set of intrinsics, we identify the common higher-level pattern and implement that pattern as a single function. We refer to this unifying function as an uber instruction. For example, we can unify all the shift-right intrinsics by defining a single function like this. This shift-right uber instruction has flags to specify optional rounding and saturating to a lower precision, as well as a flag to specify whether we want to compute a logical or arithmetic shift. Similarly, we can unify all multiply add instructions by defining an uber instruction that takes a weight matrix and convolves the input vector with the provided weights. By providing different weight matrices, we can implement any sequence of multiply add operations. Once we have derived the set of uber instructions, which we refer to as the uber instruction IR, we can reframe the original code decomposition problem as a code rewrite problem. In other words, to decompose this input expression, we simply rewrite it using the uber instructions that we have derived. This gives us a two-stage algorithm for instruction selection, where in the first stage, the input expressions in the compiler's IR are lifted to higher-level uber instruction IR. Then, each uber instruction in the lifted expression is lowered to an optimal executable instruction sequence in the target instruction set to generate the final expression. The first lifting rewrite is performed using a greedy operator packing algorithm that resembles traditional instruction selection approaches, such as maximal munch. The key difference being that we do not rely on predefined rules, but rather query a synthesizer at each step to determine when the operators can or cannot be packed together in the same tile. To understand how the lifting algorithm works, let's apply it to our running example. There are three steps to the algorithm: fold, replace, and extend, that are applied repeatedly until the entire expression is lifted, starting with the first operation. Given this cast operator in the input sequence, the first step is to try to fold this operator into the last uber instruction in the lifted expression. Since the lifted expression currently has no uber instructions, we move on to the next step, which is replace. In the replace step, we try to replace the last uber instruction in our lifted expression. Once again, there is nothing to replace yet, so we move on to the third and final step, extend. In this step, we synthesize a new uber instruction that can represent this operation and add the synthesized uber instruction to our lifted expression. In this step, the synthesizer returns the cast uber instruction with the rounding and saturating flags set to false. Now, with the cast operation lifted, we move on to the next operation in the sequence, which is the shift right. Once again, the first thing we try is to forward the shift right into the last uber instruction in the lifted expression, which is the cast uber instruction. We may try to do this by flipping the rounding or the saturating flags, for example. Since this is not possible, we then try to replace the last uber instruction in the lifted expression, meaning we try to replace the cast uber instruction with a different uber instruction that can represent both of these operations. The synthesizer returns the shift right uber instruction with the saturating narrow flag set to true. Note that the synthesizer is able to reason about the semantics of this and is able to determine whether this transformation is or isn't safe to do so. The next operation is the addition by 8, which can be forwarded into the current uber instruction by simply flipping the round flag. This process then iteratively continues, greedily packing and folding as many operators as it can into the last uber instruction until all operators have been lifted, giving us this final expression. Since this is an algorithm that greedily packs operators, it does not guarantee that it will find the shortest sequence. However, the uber instruction IR is a much higher level IR than the target instruction set, making it much easier for the greedy algorithm to converge on the best representation. Furthermore, the greedy algorithm is scalable, which is important as the input expressions may be arbitrarily large. Once the input expressions have been lifted to the uber instruction IR, we use exhaustive search guided by a cost model to lower each uber instruction to its optimal implementation in the target instruction set. A key challenge while lowering to the target instruction set is that to find the best performing implementations, we must explore implementations that contain both computation and also data movement. Powerful fused intrinsics offered by modern architectures are often restricted to certain input and output data layouts. For example, on this slide you can see the VTMPY instruction from Qualcomm's HVX architecture. This instruction is extremely useful for implementing 3-element wide sliding window reductions. The color scheme in this figure highlights the flow of data from the input vectors at the top to the output vectors below. Notice that not only does this instruction have a really unusual read pattern, but it computes the output in a deinterleaved format. Using instructions such as this one often requires swizzling either the input or the output data, sometimes both. And the increased throughput offered by these intrinsics can often justify the overhead of the introduced data movement. Therefore, during the lowering stage, Rake decouples the synthesis of computation from the synthesis of data movement. This is done by first synthesizing a swizzle-free sketch, which is a partial implementation that uses concrete intrinsics to represent the computation, such as VAdd, but uses special constructs to represent arbitrary data movement. This decoupling allows Rake to scale and explore a much richer set of implementations. In this example, we have a swizzle-free sketch that uses the fused HVX intrinsic to perform the rounding saturating shift right narrow operation. However, since this instruction produces interleaved output, we must deinterleave the input vectors to undo the implicit interleaving and get the output in the right layout. When synthesizing swizzle-free sketches, we represent data movement such as this as a hash table that maps each lane of the swizzled vector to the input value that it must contain. In other words, to prove that the sequence of compute intrinsics can produce the correct output, we synthesize a valid swizzle over which the output is correct. Figuring out how that swizzle can be implemented optimally using the available intrinsics is deferred. Synthesizing these hash tables to represent data movements is much easier than synthesizing the sequence of instructions that perform that data movement. Primarily because this can be done incrementally. For example, rather than compare the entire outputs of the synthesized and the input expression, we can, as a filtering step, compare just the first 4 elements of the generated output vectors. This is a necessary condition for correctness and will fail for the vast majority of obviously wrong candidates in our search space. To prove this necessary requirement, we only need to synthesize hash tables that describe what data must be contained in the first 2 lanes of the swizzled input vectors. Synthesizing such tiny hash tables is cheap and allows us to quickly eliminate the vast majority of bad solutions. One challenge of this decoupled approach is that when synthesizing the swizzle-free sketches, we can only generate the cost lower bound, which is essentially the cost of the compute intrinsics, as we do not yet know what the cost of the necessary swizzles will be. The sketch with the smallest cost lower bound may not necessarily yield the implementation with the lowest final cost. Therefore, we allow our algorithm to backtrack, using the cost of the generated implementation as a constraint to refine the search space and generate better implementations. To evaluate our instruction selection algorithm, we compare the runtime performance of 21 benchmarks that generate a total of 450 expressions. These benchmarks include common image processing operations, the Franken-Camera pipeline, halide implementations of various TensorFlow neural network layers, and other key workloads such as quantized matrix multiplication. As a baseline, we compare against halide's highly optimized HVX backend, which uses a combination of LLVM's instruction selection and super optimization, as well as a corpus of handwritten rules that were prepared by Google and Qualcomm engineers over the years to fill in the gaps of the LLVM's instruction selector. It is important to note that we compile both implementations with the exact same schedule, the only difference being in the instruction selection. This figure summarizes the results of our experiment. On the y-axis, you can see the speedup observed by using our instruction selection algorithm over halide's backend. 10 of the 21 benchmarks show non-trivial performance improvements, with speedups as high as 2.1x in the case of the Gaussian blur. Another 10 benchmarks showed identical performance, and only one benchmark showed a performance degradation. Upon manual inspection, we realized that this was not due to worse instruction selection, but rather because halide's instruction selector has the ability to alter scheduling decisions, such as changing the layout of an intermediate buffer. This kind of scheduling optimization is currently outside the scope of Rake. On average, Rake was able to improve the performance by 18% across all benchmarks simply through better instruction selection. The mean compilation time per benchmark was about an hour. Moreover, our experiments demonstrated that Rake can successfully scale to even very large input expressions, such as this expression from the Franken-Camera pipeline. Rake can also generate really large instruction sequences, such as this HVX implementation from the quantized matrix multiplication benchmark that contains over 100 intrinsics. This benchmark demonstrated an overall speedup of 70%. Moving forward, the most important question we want to ask is whether we can memoize the transformations we discover through Rake. Despite our many optimizations, synthesis remains an expensive process. Effective memoization could prevent us from having to use this expensive process for patterns that we have already seen and optimized before. In addition, we are also actively working on extending Rake to support other vector instruction sets, notably ARM and AVX2. Though this is still ongoing work, early results indicate that the set of Uber instructions required to do instruction selection for these backends is remarkably similar to the one that we use for Hexagon's HVX backend. To sum up this talk, we present a new instruction selection algorithm called Rake that lifts input expressions into an Uber instruction IR before lowering them to the target instruction set. Rake decouples the synthesis of computation and data movement to make the lowering phase tractable. Our results show that Rake can outperform halide's professionally developed instruction selection algorithm by 18% over 21 real-world benchmarks. Thank you for your time, and now I will take any questions that you have.